Alrighty, good morning everybody. Welcome back to Calc 2. Plan for today, as promised, I have a Standard 2 quiz ready for you. And then we are going to get into Standard 3 and talk about another integration technique called integration by parts. As far as office hours go, my next office hours will be on Mondays from 11 to noon and from 1 to 2. So this is another homework assignment, homework 4, which will be due on Wednesday. Don't forget you have web work homeworks due tonight as well as Monday night. Graded some retests, so go ahead and pass those back. Anna? C. Sarah? Reagan? Go ahead and pass that over here. So, you're right there. That's right, you're not sitting there anymore. So you used to be sitting there, I'm like, absolutely.
I know I'm also used to sitting there. It's a different angle of the classroom.
Sorry, Keith. Caleb. And Joe. Alrighty. Any questions or comments before we get started with today's quiz? Why is it a bad idea to try and teach horses analytic geometry? You should never teach horse analytic geometry because it's not wise to put Descartes before the horse. And with that, go ahead and pass out today's quiz. So same as last time. When I say go ahead and take a few seconds to finish up your thoughts, that's your 45-second warning. Have fun. You got this. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Something I always do when I challenge myself on my stopwatch, I try and stop exactly on the second I intend. I got accurate to within 100th of a second. Pardon me. Alrighty, time then for standard 3. Okay, so standard 2, we talked about use substitution quite a bit, where use substitution was our method for undoing the chain rule, so to speak. Oh, that's why there's so many of these. If your packet says density at the top, you accidentally got a different classes. So, these are getting mixed in. Thank you. So raise your hand if you need a new package. Okay. Also, pass your density. Hand it again. And go ahead and pass your density packet back up to the front of the room, please, because I'll need that for my stat class. There. I was wondering why I had so many of these left over. We're not doing density in this class, although it's a fun topic. So standard 2, we talked quite a bit about how to undo the chain rule. In this standard, we're going to be focusing instead on how can you undo the product rule when it comes to integration. And the technique we're going to use is called integration by parts. So to start with, I'm going to take a look at the product rule and see how can we change our product rule formula somehow from a differentiation formula to an integration formula. So the main idea behind the product rule is you're looking at two different functions being multiplied together. And when you want to differentiate their product, f of x times g of x, typically what the product rule would tell you is that you would do first function, f of x, times derivative of the second function, added to the derivative of the first function, f prime of x, multiplied by just plain old g of x. And typically, that is how you would write out the product rule in terms of differentiation. So, here's my question for you. how can we take this formula, which says something about derivatives, and find a way to do something to both sides to make it an integration formula? Well, we want integrals to be showing up on both sides. Aiden, what can we do?
Integrate it.
Yeah, let's just integrate both sides with respect to x. And if we do that, what do we get if we take the integral of the derivative of f of x times g of x? What would we expect to happen if we integrated the derivative of f of x times g of x? Bethany?
Wouldn't we just get f of x times g of x?
Yeah. Integration, or an indefinite integral, is kind of the inverse operation of taking a derivative. You're finding anti-derivatives of the derivative. Well, anti-differentiation and differentiation should cancel each other out. So what we'll be left with is just f of x times g of x. Plus c. Technically, we could also get an extra constant term when we do our indefinite integral. So the way we can write that is we can say integrating both sides that's going to give us, on the left-hand side, we'll be left with f of x times g of x. And on the right-hand side, we'll have the integral of f of x times g prime of x plus f prime of x multiplied by g of x. But Dr. Gerstle, what happened to the plus c? This plus c here, we can actually ignore, because when we integrate the right-hand side, it'll have a constant term as well. It'll have its own sort of plus c going with it. So we can just kind of subtract this, we can just kind of combine this constant term with the constant term we would get from this integral, and just combine them into one super constant term. No, super constant term doesn't mean anything, I just made it up. So I'm going to take this right-hand side, split it up into two separate integrals. Integral of f of x times g prime of x dx plus the integral of f prime of x times g of x dx. Because while integrals don't break up nicely over products, they do break up nicely over sums and differences. Integral of a sum is the sum of the integrals, etc. And finally, what we're going to do is I'm going to take this equation right here, this f of x times g of x equals integral plus integral, and I'm going to rewrite it a little bit. I'm going to put this term on a side by itself by subtracting this other integral from both sides. So what we would be left with, if we wanted to solve for this, is integral of f of x times g prime of x is going to be equal to f of x times g of x minus the integral of f prime of x times g of x dx. Everyone on board so far? A lot of playing around with derivatives and integrals here, but just kind of really all that we're doing is we're taking the product rule formula from Calc 1 and integrating both sides and then moving around some of the pieces a little bit. All right. Now, we're going to make a u substitution. What I'm going to do is I'm going to let u represent f of x, which would make du equal to dx equal to, well, just f prime of x or du equal to f prime of x dx. And once we make our, and we're not just going to do a u substitution, we're going to get a little bit frisky with this one. We're going to do a v substitution as well. And let v be equal to g of x, which will make dv dx equal to g prime of x, or dv equal to g prime of x dx. And what we'll be left with after we do a u substitution as well as a v substitution is if we kind of take a look at each of our pieces, we have f of x is going to become u, g prime of x dx is going to become our dv, f of x is u, g of x is v, g of x is still v, f prime of x times the dx term, these will combine to give us a du. And what we'll be left with when we rewrite our entire integral in terms of u's and v's is going to be that the integral of u dv is equal to uv minus the integral of v du. Or as Dr. Gabler would put it, the integral of u dv is going to be ultraviolet minus the integral of voodoo. And this formula right here is our reverse product rule, which we're going to give the more fancy name of saying integration by parts formula. P and parts doesn't need to be capitalized. So ultimately, what this formula is going to give us is it's going to give us a way of taking an integral that's written in this form, integral of u times some dv, where u and v are going to both be kind of terms that get involved in a substitution. And it allows us to rewrite it as whatever u times v is minus a different integral, this time the integral of our v term times du. And ultimately, what this formula is going to allow us to do is it's going to allow us to take one integral that is scary and hard to do, but we're going to replace it with an integral that's hopefully easier to work with than the initial integral. So before we go into some examples, anybody have any questions or comments about how we got this formula? Awesome possum. So let's see how this is useful. Let's see how we can actually use this. So, me on the second page, let's say we wanted to look at the integral of x times cosine of x plus 2. So, let's say we wanted to try and solve this integral by u substitution. Would anybody like to propose what we could try to do for a u term if we wanted to do some u sub on this bugger? Reagan, what would you try for a u first?
You could equal x plus 2.
Yeah, because it sort of looks like we have multiple things going on where we have an x plus 2 inside of a cosine. Usually when we're working with u sub, that's oftentimes a surefire sign that, like, hey, that inner expression, the x plus 2, should be, I don't like using this as an example because I just realized we could do this one with u sub. Well, let's look at why. So, if we let u be equal to x plus 2, we'll get du dx is, well, I think that's just going to be 1 if we differentiate x plus 2 on both sides, which will make du equal to dx. So what we'll end up with is an integral of, well, we'll have a cosine of u, we'll have a du term, and we'll have an x. So what's up with this x term? Jonah?
Well, if you do x equals u minus 2.
Yeah, if you're sneaky about it, you can actually get around this and say, oh, let x be equal to u minus 2. So you get u minus 2 times cosine of u du.
Then you
Okay.
still end up with a
Which means we can rewrite this as u cosine of u minus 2 cosine of u. I know how to integrate that. Integral of cosine is just going to be sine of u, or negative 2 sine of u. How do we integrate u cosine of u? Do we have, is that something that we have a nice formula for? Don't really think so. So this would be an example of an integral where our good friend u substitution is going to fail us. So sadly, trying to do a u sub, and Reagan, I agree, I think when I look at this integral, if I were to do u sub on it, x plus 2, I think is the natural choice for u. And it kind of gets us to a dead end, where we end up needing to integrate u cosine of u, and it's not super easy to work with. What we're going to do instead, we're going to listen to Dr. Gabler talk about something for a second until I close the door. And now that we've shut out that distraction, shout out to Dr. Gabler, he's not a distraction, he's a good guy. We're going to try this new technique instead, this integration by parts. And our goal when we're doing integration by parts is we'd like to look at the initial integral, in this case x times cosine of x plus 2. And what we're going to do with this is we're going to break this integral apart into a u term and a dv term. I'll do this one to kind of show you how I would go about thinking about this. But for the next, and then we'll do a couple more examples where I'll let you all decide how you all want to do the integration by parts. So here's what we're going to do. I'm going to let u be equal to plain old x, and let this term become the u in our integral. And we're going to let dv be equal to cosine of x plus 2. That'll allow us to take our initial integral and write it in the form integral of u dv. Oops, forgot my dx. So here's a question. If u is equal to x, what would that make our du equal to? James?
dx.
Yeah. We would get that du dx, the derivative of u with respect to x, well, that's just going to be 1. So du would be equal to dx. And here's the tricky one. If dv is equal to cosine of x plus 2 dx, well, that would naturally mean that we'd get dv dx is equal to cosine of x plus 2 And if dv dx is equal to cosine of x plus 2, what's that going to make v equal to? So in other words, what function is going to have a derivative of cosine of x plus 2? Jonah?
The sine of x plus 2
The sine of x plus 2.
plus c.
By the way, Bethany, I totally see you back there. I'm just trying to spread the answers around just a little bit. So, yeah. In general, if I try not to call on you, it's because I'm trying to spread around the answers a little bit in class, just to get more into the class involved. No, nothing personal. Okay, so Jonah said, okay, what function has a derivative of cosine of x plus 2? How about sine of x plus 2? If we differentiate sine of x plus 2, we'll get cosine of x plus 2 after all. Technically times the derivative of x plus 2, but that's just times 1, so nothing changes. And what we're going to do is we've taken our initial integral, we've written it in the form integral of u expression times dv expression. According to our integration by parts formula, the ultraviolet minus the integral of voodoo, we can write that as u times v minus integral of v du. Or using what we've discussed so far, or the term so far, our u is equal to x. Our v is equal to sine of x plus 2 minus integral of v, which is sine of x plus 2, times our du term, where our du term is just going to be plain old dx. Okay? Well, we've taken one integral and we've rewritten it in something plus a different, or technically something minus a different integral. Here's a question. Is sine of x plus 2 any easier to integrate than x times cosine of x plus 2? Rhoda, I see you nodding along. How would you integrate sine of x plus 2?
Then we could just do normal u substitution and put u as x plus 2.
Yeah, we could either do another u substitution, or we could, if we recognize, oh hey, I know how to integrate this, we could just do, that becomes integral of plus cosine of x plus 2. And at the end, since we're doing some indefinite integrals, we'll need our plus c term. And it turns out that is our final integral. Integral of x times cosine of x plus 2 is equal to x times sine of x plus 2 plus cosine of x plus 2 plus c. So what on earth did we do here? We started with an integral that we could write as a product of two different terms, an x term and a cosine of x plus 2 term. And what we ultimately ended up doing is we differentiated one of these terms, we differentiated the x, we integrated the other term, the cosine of x plus 2 term, to go from an integral of u dv to integral of v du. And it turns out that when we differentiated this, the u piece, and when we integrated our dv piece, we ended up with an integral that's a lot easier to actually go about, integrating than the initial integral was. And we did that via this sort of double substitution where part of our initial integral becomes u, another part of our initial integral becomes the dv piece, and that is integration by parts in a nutshell. So, Nolan, how can we check check our answer. Make sure we did everything correctly without going back through each step.
Find the derivative of your answer and see if it equals x cosine x plus 2.
Yeah, we can check ourselves by differentiating our answer here. And hopefully we end up back with the function we started with, the x cosine x plus 2. So if we differentiate x times sine of x plus 2 plus cosine of x plus 2, and technically plus c. Phoebe, what rule would we need to use in order to differentiate x times sine of x plus 2?
The product rule.
Yeah, that looks like we're going to need a product rule. We have an x piece, we have a sine piece. So we would have to do a product rule to differentiate that. So if we do that, we'll get first term times derivative of the second term, which is x cosine of x plus 2, plus, and here we're using the product rule on this, the derivative of the first term, x, which is just going to be 1, times the second term, sine of x plus 2. Joy, how would we differentiate then this cosine of x plus 2 term?
You would take, since the derivative of sine is cosine, so.
Derivative of positive sine is positive cosine, so the derivative of positive cosine would be
Negative sine.
negative sine. Yeah, so we'll have a minus sine of x plus 2. And then the plus c term, it just has a derivative of 0. Devin, is anything going to cancel out for us here?
Sine x plus 2 and negative sine x plus 2.
Yeah, we have plus sine of x plus 2, minus sine of x plus 2. I think we could do the old swoosh swoosh on those, because they cancel out. And we'll be left with x cosine x plus 2. Nolan, is that what we wanted to get? Neato Dorito. So just like how standard U substitution from standard 2 gave us a way to sort of undo the chain rule from Calc 1, integration by parts, this sort of double substitution, is going to give us a way to help us undo the product rule. Because in order to differentiate our final answer, the product rule is what we needed. So that's going to give us kind of another way to undo one of our differentiation rules from Calc 1. Let's pause for a second and see what questions or comments do you all have about this. It's definitely something I would consider to be a bit of a trickier technique than U-sub. Which is why we did U-sub first, because U-sub we just do sort of a single substitution, integration by parts, we end up with a double substitution that ends up happening. Yeah?
Kind of seems like us being able to do this problem hinged on the fact that like cosine of x plus 2 just happened to have a really easy derivative, which was sine of x plus 2. If it was like x times cosine whatever, messing this aside, like
X times cosine, give me something scary.
even just like x or something where you'd have to like also do an extra u substitution to derive or to integrate the chain rule inside of the cosine.
So
You see, like we had like dv over dx equals cosine, so we're like, okay, what would give us that as a derivative? So we're just like, oh, it's easy, it's sine of x plus 2. But what if it was like, yeah,
how would we deal with something like this? Well, we might need to do an integration by parts and U sub combined to deal with something like that. And don't worry, we'll see some examples of integrals that end up looking like this. So in this case, having just plain old sine of x plus 2 and cosine of x plus 2 made this a not super complicated example. But you're definitely right, Gabe. It can get a lot more complicated if you have nastier expressions that kind of are going inside and outside of various pieces. Good observation. Sometimes we'll need to have, sometimes we might need to use substitution and integration by parts combined, as we'll later see. By the way, by the end of standard 4, I'm going to have an integral for you all that you'll need to use like 6 different integration techniques on. It's going to be fun. I'm looking forward to it. Let's do another example. How about, and this time we'll do one with a definite integral. Let's do a definite integral from 1 to 2 of x cubed times natural log of x dx. Nora, if you were to try and do a u substitution on this integral, do you see any obvious choices for what might be a u for us?
Then maybe x cubed.
If we had u equals x cubed, we have our du ends up being 3x squared dx. And is that any easier to work with?
No.
Doesn't seem super helpful. Okay? Because then how do you deal with the natural log of x term? Okay? If u is just natural log of x, then we'll get du equals, what, 1 over x dx, and how do you deal with the x cubed term? So just doing a single u substitution by itself, I don't think is going to be super helpful for us here, unfortunately. So I'm going to give this one a go by parts. Would anybody like to propose a way that we can take our initial integral, x cubed times natural log of x dx, and split that up into a u piece that we can differentiate and a dv piece that we can integrate? Bethany?
So we could make u ln of x and dv the x cubed.
X cubed dx, like that? James, is that what you were going to suggest?
I was actually going. Oh wait. Yeah, that's what it was.
Okay then.
Yeah.
As I said, the dx needs to be attached to the dv. So the real question is x cubed going to be part of the u term or the dv term, and the natural log of x would just go along with the other one. All right, if u is equal to natural log of x, Katie, what would that tell us about du?
Would be 1 over x
Give me 1 over x
and then dx.
dx. So we can differentiate, we throw a little arrow going down for differentiate to get from u to our du term. How about if we went the other way and integrated our dv term to get to a v term? Ty, what would that give us?
X to the 4th over 4.
Yeah, that's going to give us a 1/4 x to the 4th. Technically, we could have a plus c, but since we're doing a definite integral here, we don't have to worry about our constant term. So, okay, so we've taken our u dv integral, where this was our u, and that was our dv. And now, we can use, or at least try to use, our integration by parts formula to write this as uv minus integral of v du, which will give us u times v is, what's that, 1/4 x to the 4th times natural log of x minus integral of v du. So 1/4 x to the 4th times 1 over x. Is this integral looking easier to deal with than the initial one? X cubed natural log of x? This 1/4 x to the 4th times 1 over x? How could we maybe rewrite this integral in a way that'll make this a little easier to work with for us? Aiden?
1/4 times x to the 3rd. You can cancel one of the exponents out.
Ah! We have an x to the 4th times 1 over x. You're proposing we just say, oh, we can just multiply those together to get an x cubed term? Sounds good to me. It's integral of 1/4 x cubed. Yeah, because, well, these two kind of might seem scary into how do you integrate x term times x term? Well, we can just combine those two first and then try integrating. Speaking of which, Mary, how would we integrate 1/4 x cubed?
What would be x to the 3 plus 1 divided by 4?
Yeah, so I'll have 1/4 times x to the 4th over 4. Or I'm going to go ahead and combine those on this line so just so I don't have to write an extra line out to do this. I think we could write this as 1/16 x to the 4th. What am I forgetting to do?
We need to plug in the endpoints, like the numbers 2 and 1 into the equation.
Yeah, we've kind of forgotten about the fact that we have a definite integral going on here. I've been a little bit sloppy with the notation. Turns out that's not a huge deal. We're just going to plug in the endpoints. This is an integral from 1 to 2. This is an integral from 1 to 2. This is evaluated from 1 to 2. And ultimately, what we'll be left with is just an expression like this where we need to plug in our bounds and subtract. So if we do that, we'll get 1/4 times 2 to the 4th. 2, 4, 8, 16 is 16. Natural log of 2. Minus 1/16 times 16. Minus 1/4 times 1 to the 4th times natural log of 1 minus 1/16 times 1. I'll move over here so those of you in the back can hopefully see it. Just going to give us 4 natural log of 2 minus 1. What's natural log of 1? In other words, e to what power is going to give us just plain old 1? Joey?
0?
Yeah, this term's just going to be 0. So we can cancel it out. So then we'll have minus 1/16. So I think we would want to add 1/16 to this. Which will give us 4 natural log of 2. And if we subtract 1 and then add 1/16, how can we write minus 1 plus 1/16? If I gave you a full pizza and then took away a 1/16 of that pizza, what would be left? James?
15/16.
Yeah, 15/16. In this case, we'll have minus 15/16. And that going to be our answer. So what's going on here? Bethany, I think I really like your initial choice of u and dv here, of trying to let the u term be the natural log of x term, dv be equal to the x cubed term. Because while u dv was hard to, this times that was really hard to integrate, natural log of x times x cubed. When we differentiated the natural log term and we integrated the x cubed term to go from a u dv integral to a v du integral over here, we actually got an integral that was much easier to evaluate because, as Hayden pointed out, 1/4 x to the 4th times 1 over x, that's something we could just multiply together to just get 1/4 x cubed, which Mary then was able to just integrate using the reverse power rule. So the whole idea, again, with integration by parts is we're taking an integral where we have two things multiplied together, and we're differentiating one of those pieces, integrating the other piece, and then we'd like to end up with an integral that's easier to evaluate, where the integral of v du it becomes something that's much easier to work with than integral of u dv. Questions, comments, concerns? All right, let's do a fun one. What would we get if we just wanted to integrate natural log of x by itself? We've talked a lot about how you differentiate natural log of x, but we've never said anything yet about how you could integrate a logarithm function. James, do you have any ideas how you would approach this one?
Would you start with writing it as the integral of x to the 0th power times ln of x dx?
X to the 0th power is 1, so sure. Is that helpful?
Well, so then it's more like the problems that we've seen in the past, where we use integration by parts.
Yeah, so this one we had x power of x times natural log of x. This one now we technically have power of x times natural log of x. Do you propose we do a very similar integration by parts to help us with that one?
Yeah.
Okay. All right, James, since you suggested it, what would you like our u to be, and what would you like our dv to be from this integral?
So you'd want the u to be the ln of x, because if you did the dv, you just have to integrate ln of x again right away.
Mm-hmm.
And then you'd want the x to the 0 dx to be the dv.
Yeah. Well, if we wanted, we could just say dv equal to dx.
Oh yeah.
By the way, that's how I approach this one, is just like dv be dx. Or you could write it as x to the 0 dx if that helps, if that helps you think through it a bit more effectively. That looks like a search. Okay. Kate. If u is natural log of x, what would our du be if we differentiate that?
1 over x. Oh, there's 2 K's.
I was gonna say, yes. Now, Calc 1, I had like 3 Kate/Katies in the class. I've lost one of the Katies, but I've gained a Kate from this semester. So now we're back to the status quo of if I say Kate/Katie, I have to be very careful. But maybe I should just split the difference and let, I don't know, Nora give the answer. You're kind of right in between the 3 Kate/Katies. Yeah, we get a du is equal to. We get a du is equal to 1 over x dx term. All right, Jonah, laugh it up. If v is equal to dx, what's our v going to be?
X.
Yeah, because Because this is like say dv dx is equal to 1, and if we wanted to ask what function has a derivative of 1, well, x has a derivative of 1. So we can actually do this by integration by parts, even though the initial integral doesn't look like natural log of x isn't getting multiplied by anything. Technically it is. It's getting multiplied by dx. And we can then write this as uv minus integral of v du. Well, our u is natural log of x, our v is x, so we can write this as x natural log of x, minus the integral of v du, that's x times 1 over x dx. Emerson, how would you propose we integrate x times 1 over x?
Well, I think it's easier if you simplify it first, because then you just get 1.
I think it's a lot easier if you do that first. So I'll give us x times natural log of x minus the integral of 1. And Carson, how do we integrate 1? Yeah, that just becomes x. So we get a final answer of x times natural log of x minus x plus c. Because we're doing an indefinite integral here. And that's how you integrate the natural log function. X natural log x minus x plus c. If you want, you can even check that by differentiating this, and you'll end up back with just natural log. All right, one more fun one, and this is a pretty quick one before I let you go for the weekend. Go to the next page. I'm going to integrate 1 over x. Now, in Calc 1, probably talked quite a bit about this one. Oh, the integral of 1 over x is just natural log of absolute value of x, her, der. Plus c, excuse me. I want to see what happens if we integrate this one by integration by parts. Let's show you this very quick. Because technically, we could do u equals 1 over x, dv equals dx. Do a quick integration by parts on this, which would make du equal to negative 1 over x squared dx. Our v would become plain old x if we do this. And if we write this then as uv minus integral of v du, we'll get uv is 1 over x times x minus the integral of v du. That's x over negative x squared dx. If we simplify this a little bit, we'll get that this integral is equal to 1 minus minus becomes plus the integral of 1 over x dx. And we end up with the expression integral of 1 over x dx is equal to 1 plus the integral of 1 over x dx. Well, I'm going to cancel out this expression from both sides, and what we're ultimately left with is that the integral of 1 over x dx is the fact that 0 equals 1. Have a good weekend, everybody. I'll see you all on Monday.